Hello, I am Michael Battalio. I'm a postdoctoral associate at Yale in the Department of Earth and Planetary Sciences, and I'm very excited to be returning to the Southeastern Severe Storm Symposium to present some of my latest results looking at large-scale extratropical convective systems on Titan, how they evolve and how they impact the entire globe's atmospheric dynamics, and then comparing those to mesoscale complexes on Earth. First of all, I just want to start off with some background information for Titan because I realized this topic of planetary atmospheres is not something that's usually found at this symposium. Titan is a very interesting world, though, because it's a moon, yet it has the second densest terrestrial atmosphere in the solar system after that of Venus. Titan is a moon of Saturn, and while its interior may have a water ocean, the hydrological cycle above the surface is one of a methane cycle because at the surface temperatures and pressures of Titan, about 94 Kelvin and about 1.5 bars of pressure, we're around the triple point for methane. So methane is in liquid form in precipitation, it's in ice form in clouds, and it's obviously in vapor form in the atmosphere. An example of this is shown in the movie on the right. As this movie loops through again, you'll note that a lot of these white cloud features start off in the movie are rather cumuliform in shape, but as time goes along, as they progress along this darker feature on the surface, as they get to the edge, they become wispy and then they fade away. That's because these are essentially lake effect methane clouds on Titan, because this dark body here is a methane sea. These are concentrated at the highest latitudes, mostly at the northern pole, but a few at the southern pole as well. The equatorial latitudes are actually quite dry, so there is a moisture gradient that's kind of reversed from that of Earth, from the pole to the equator. That'll be important later on. An additional important difference between Titan and Earth is that Titan rotates much more slowly than Earth does at about 16 days. So it has an extremely large Rasby number on the order of 10 or so. That means that the tropical latitudes, quote unquote, for Titan extend very close to the pole, and the extratropical latitudes are poleward of about 70 or 75 degrees north. What about extratropical storms? So these small wispy cloud features are associated with Rasby waves, so high latitude extratropical waves on Titan. And you'll note that the wind seems to be blowing through these waves faster than the motion of the clouds as a group are progressing. So these are indeed Rasby waves. The waves are propagating westward relative to the mean flow. So all of these images I've shown you so far from Titan are all taken from the Cassini orbiter, which is mission ended in 2019. Unfortunately, it never caught a big convective event during one of its flybys. To look at one of those, we must rely on observations of Earth. So these observations are taken from the Keck Observatory in Hawaii, and this top panel just shows some regular convective activity bubbling along at the southern pole of Titan. However, in 2004, for one particular month, there was this enormous convective event in the southern hemisphere. If we were to scale up this convective event to Earth, it would be like a mesoscale convective complex that was like the size of Asia or something like that. So these aren't actually mesoscale convective complexes, but synoptic scale convective complexes. Even more curiously, if you project these clouds onto the globe, the clouds don't actually move, even though the planet kind of rotates beneath them. So even though it's traveling waves that instigate this activity, the events themselves, the large convective events at least, seem to be stationary. Why is that? Hopefully I'll be able to explain this over the course of the presentation. You may now be asking yourself, though, so what? Who cares about Titan? We still don't understand completely all of the nuances of Earth's atmosphere. Why study planetary atmospheres in general anyway? Well, the so what is because NASA is going to be sending the Dragonfly quadcopter to Titan in 2035 or so. And this will be answering, or at least addressing, many questions for prebiotic chemistry in the solar system. For example, how life formed from a basic hydrocarbons and amino acids. Additionally, it will look for life in the subsurface ocean and hopefully understand the progression of dunes and its surface atmospheric interactions. So because this is a quadcopter, we need to be able to predict with some skill the kind of weather and atmospheric features this thing is going to encounter while its prime mission is ongoing. Unfortunately, though, for Titan, we don't exactly have a reanalysis data set to draw upon. So basically, all of the atmospheric studies that are done for Titan are done using model simulations. And for this study, I'll be using what I would argue is the most advanced GCM for Titan, the Titan atmospheric model, which was developed by my advisor, Professor Juan Laura at Yale, back when he was a graduate student at the University of Arizona. I won't go through all of the details of the model. I invite you to read these papers that are out in the literature right now if you'd like to know more, but it's based on the GFDL flexible modeling system. We have to run at a pretty coarse resolution because to get any sort of interannual variability, we have to run for a really, really, really long time. And so it makes these data sets pretty large. Therefore, we have to have, as you might expect, a convective parameterization to simulate convection in the first place. And we use a simplified Betz-Miller scheme documented in JAZZ by Frierson in 2007. It's a great paper if you're interested. Convection happens in two modes in the scheme, and they both happen when CAPE minus sin is greater than 0. The shallow convection, or non-precipitating mode, happens when you can stabilize the vertical temperature profile simply by mixing everything together without having to resort to any sort of latent heating transfer. Deep convection, and therefore precipitation, happens when you can only stabilize the profile by changing the enthalpy of the system by releasing latent heat. When you do that, you adjust back to a pseudo-adiabat, and all that latent heat you release, you just let fall to the ground via precipitation. So with that, we can actually look at these individual events. But instead of looking at just one or two case studies, I think it's better to look at a composite of lots of events together. So we'll composite over this entire 15-year data set by picking out instances of greater than 90th percentile precipitation, and then identifying at those time steps the eddy surface pressure maximum, and then rotating the grids and the globe beneath that so that everything lines up at the same relative longitude of 0. In the Northern Hemisphere alone, over these 15 Titan years, there are 48 events, so about 3 events per year. And these events all occur in the summer. The Southern Hemisphere is pretty similar to the Northern Hemisphere, but for brevity's sake, I'll only talk about the Northern. I first want to compare and contrast this, though, to environments that we find mesoscale convective complexes, though, on Earth. So these next couple of slides have figures taken from Song et al. 2019, which is in the Journal of Climate, looking at and compositing over environments that favor mesoscale complexes in the Great Plains and southeastern United States. A couple of ingredients are important, as you would expect. First of all, you need anomalously large surface moisture at the low levels, and in the upper levels, you need a source of forcing to bring in these moisture fluxes and heat fluxes. And the source of this is anomalous high geopotential over the Great Lakes. What this dynamically means is that you get large divergence in the upper levels and the initiation zones for these mesoscale complexes as well. So you need both warm air advection and you need moisture advection. And you get both of these by having the single synoptic scale high pressure system bringing in moisture and heat from the Gulf. The thermodynamic environments, as you might expect, they have to be really unstable, so anomalously high CAPE over 500 joules per kilogram over kind of a climatological value of CAPE in the southern plains. Additionally, though, you need to reduce the cap as well, so you have to reduce the sin as well. So anomalously low sin is also a characteristic feature of mesoscale complexes on Earth. In comparing to Titan now, I want to start off with the temporal evolution of these large mesoscale convective complexes. So what you're looking at here is a Havmöller taken from 40 degrees to 80 degrees north and averaged together so that we get this time evolution of the waves in the Northern Hemisphere. Before the event is at the bottom of the panel, and you step forward in time by going up the panel. Each of the panels are indicated with the shading at the top and then what the contours mean in each panel as well. So first of all, I'll point out that we did composite things correctly because the precipitation happens mostly at a longitude of 0, and the surface high pressure happens at a longitude of 0 as well. T of 0 is where the event happens. It's right in the middle of the figure. Before the event happens, though, you'll note that there are these regular wave trains of eastward moving waves. This is kind of a surprising result, right? Because we're averaging over 48 events. So what this means is that regardless of whatever longitude the convective event occurs at, you need a specific wave number. In this case, zonal wave number 1. So there's one trough and one peak in every single variable from west to east. You need a specific period of waves. In this case, it's about 2 Titan days or T-sols. And remember, a Titan day is about 16 Earth days. So these waves are actually very, very slow compared to Earth waves. Not only that, you need a particular phase and amplitude of the wave as well. This is kind of remarkable. It means there's only a specific type, kind, and period of wave that triggers these events. Once the event happens, everything gets kind of messy, but once everything settles back down, the waves just return to how they were behaving beforehand. To look more carefully at what's going on here, let's zoom in. Here are once again the eastward waves. So the bottom is only 5 Titan days before the event, 0, and then 5 afterwards, and then 10 afterwards. A few things should stand out immediately. First of all, when the convective event happens, shown here in the rightmost panel, along with the Cape minus Sin, this convective event occurs, it overturns the entire hemisphere of Cape, so that by the end of the event, the entire northern hemisphere has been scoured of Cape after about 2 Titan days, so about a month in Earth time. When this is going on, the wave is held in place by the strength of the convection. You can see that in any of the other variables. In the surface pressure, the wave remains steady, temperature and meridional wind to some extent as well. After the event dies off, though, the wave just starts propagating back to the east once again, just as it did before. However, something really interesting happens after about 2 more Titan days, seen most clearly, I think, in the eddy meridional wind. The wave stops moving to the east and then starts moving back to the west again until the wave kind of decays back down and things start moving back to the east again. A couple of other important features to point out. First of all, when the event is ongoing, there are also strong eddy heat fluxes and eddy momentum fluxes. So this wave is mixing up the atmosphere as well and transferring momentum into the jet. So the jet speeds up when one of these events happens. Another additional interesting feature is that, so I've said now that these are zonal wave number waves. There's one trough and one crest in every single field from west to east, except for the thermodynamic variables. In the Cape, there are 2 crests and 2 troughs. So what's going on here? So remember I said earlier that the gradients of moisture and temperature are opposed on Titan. It's moister and colder at the pole and drier and warmer at the equator for Titan. So if you think about what causes Cape to be large, you can either have really large moisture and or really high temperatures at the surface. So there's these competing effects of high moisture right here, lining up with this maximum in the Cape minus Sin, and this area, which is high eddy temperatures, lining up with this area, high area of Cape minus Sin. Now, the important thing to note is that the gradients of moisture are larger than the gradients of temperature. So the eddy moisture is more important than the eddy temperature, and that's why the event lines up with the area of Cape that's associated with the eddy moisture fluxes. So this is very different from how Earth operates, in that you only need one flux, only one direction of air transport to get everything, all the ingredients that you need for these complexes. On Titan, it's a bit more complicated than that. First, though, let's delve into why these waves switch back and forth going west to east. And to do that, all you need to know is that these are Rasby waves. And we know that by plotting the dispersion relation for Rasby waves against the wave number versus period spectra for these simulated events, and they line up perfectly. So these really truly are Rasby waves. And if you think back to those dreaded dynamics classes, if you've had them yet, remember that the only way you can change the phase speed of Rasby waves down here, this is the only equation I'll show, I promise. The only way to change the phase speed of Rasby waves is to change the background wind speed, i.e. the jet, or change the total wave number of the wave, the size of the wave. Remember, the larger a Rasby wave is, the faster it propagates to the west. And when you do this calculation for these Rasby waves, you'll note that they're eastward where they should be eastward, and westward where they should be westward. And this westward movement is because the waves become so large that it overwhelms how fast the jet is moving. The stationary feature happens because the convection forces it to be that way. And this brief period of eastward motion happens because of those large momentum fluxes that I pointed out in the Havmøller in the last slide. The jet gets so strong faster than the wave gets large enough to propagate west. So you have these weird competing effects, but it's perfectly explained by Rasby wave theory. So what is the structure of this actual wave horizontally? So this movie will loop several times, and you'll see what happens as the wave progresses in time. And keep in mind this picture of the opposing gradients of moisture and temperature for Titan. So, for example, to the east of high pressure systems, you have cold, moist air advection. So it's cold and moist and pulls this air all the way around to the upwind side of the high pressure system. When that happens, this moist air that's looped all the way around the high pressure system gets drawn back into the inflow area right here of the convective event. And so you're pulling moisture back into the upwind side of the event, and so it remains stationary with time. Not only that, as this loops one more time, I'll show that the divergence at the surface caused by how strong the convection is throws mass from the northern hemisphere into the southern hemisphere, and you get this sympathetic sort of response in the Rasby waves that happen. So the wave grows to enormous size, and therefore it lasts long enough to completely scour the entire northern hemisphere of Cape. Now, because the jet moves at different speeds from the northern and southern hemispheres, the waves split apart with time. Compare this now back to the relationship that we saw for Earth, which is that you only need one high pressure system drawing in moisture and warm air from the south, and that's it. Whereas on Titan, you need this warm air advection from the equator, and you need this moisture to wrap back around again the high pressure system to really hold this event in place. I've mostly been talking about these have all been surface or near surface fields so far, so I just want to touch on the vertical structure before I end by noting that here on the right panel, this is the contours are the direct convective tendency from the model. So this is just latent heating because of convection aloft, and cooling near the surface, again, because of convection and evaporative cooling. And these set up eddy warm temperatures aloft and eddy cool temperatures near the surface. And if you think about what should happen with the geopotential heights as a result of that, you get stretching of the vertical column here and shrinking of the vertical column here. You set up these high and low pressure systems, this high pressure system you've been looking at several times now in these movies, but you also get this complicated tilted Rasby wave structure aloft. So I'll end just by reminding you that this is all for understanding the impact of what's going on near the surface for the Dragonfly craft, which will be at the equator. And so we can expect to see large changes in the RMS surface pressure and even in the thermodynamics. So this is going to be a source of a lot more study in the future. Relevant for Earth studies and astronomers is that these convective events are so large, they change the outgoing long-wave radiation by 0.5%, which will be easily observable for Earth. And we're trying to motivate some astronomers to look for this directly. So I'll close by saying, hail state, and also please contact me with any comments or questions you might have. Here's my contact information. I look forward to the Q&A. Thank you.